Okay, so what we're looking at here is a portable XRF device. You see it here, it's like a gun, which we have placed on a stand, on top of which is this platform. But really, this small field at the top is the area over which you place any number of objects. And it can analyze just about anything, and what it does is basically shoots X-rays, a very focused beam of X-rays, and does this at an atomic level. So you have your atom with a nucleus, which is orbited by electrons. These electrons are in different levels of orbit that basically create what we call these shells. And what happens is it penetrates these shells with the XR, or X-ray stream, which makes electrons kind of jump from one shell of orbit to another. When that happens, there's also an escape X-ray that is detected by the machine. And that basically gives an elemental signature of whatever the object is. Now so let me demonstrate. This is a set of flint Canadian blades from an EV1 site that we excavated recently. Throw this up on top. Start. And we run this for 2 minutes. It can run anywhere from 30 seconds to 3 minutes, more, less. 2 minutes is what we've been using. It seems pretty good. Now this gives us two things on the computer. It gives us a spectral set of data, which is basically just a visual representation of all the different types of elements. You can see it here. I don't know if it will show up. And you get these different peaks according to different types of elements. So that's the most useful real-time set of data, but it's qualitative data. We can also quantify the data to see the parts per million of each of the different types of elements, but that requires quite a lot of calibration, which is generally done at the end of acquiring a huge set of data. Now everyone gets excited about XRF because they just imagine that you can point and shoot and determine what anything is made out of. You can to an extent, but what it tells you is what stuff is in it, not exactly what the thing is. And it's of limited value to just go around shooting random stuff. What this can do, and can do well, is to take a set, an assemblage of like material, for example these Canadian blades, analyze them, and then once you've calibrated the data, determining patterns within like materials. And that's what it's most useful for, especially with obsidian. And here I think it will be very useful for flint. That's it.